This study looked at the different warm-up protocols and their influence on vertical barbell velocity in the conventional deadlift. The conventional deadlift is universally praised among strength coaches for its ability to build and assess a client's overall body strength. The deadlift is also considered the ultimate test in competitive powerlifting, being both the heaviest and the chronologically last lift at competitions. The deadlift is often the deciding effort for competitive placement. It is crucial then that components of this movement be closely controlled and enhanced where possible to ensure optimal performance. Currently, little research exists on the topic of the deadlift. Deadlift style, barbell type, ground surface, resistance type, and different resistance loads are the sole variations so far explored in scientific literature. To begin then, we look at the major component of the deadlift, power. Anatomical power is the combination of speed and strength and can be measured in many different ways. In reference to the deadlift, power is effectively analysed by studying the vertical linear velocity of the barbell during the concentric phase of the lift. Where the barbell suddenly decreases in velocity is referred to as the sticking point, and this is responsible for reduced efficiency or failure of the lift. If power can be optimised, the potential to overcome the sticking point is also improved. The sticking point involves the upward momentum of the barbell momentarily decreasing or fully halting. According to a study by Hales, Johnson and Johnson, this point is particularly important since the success in weightlifting relies on a continuous motion of the barbell past this region of the lift. The study then goes on to state that the conventional deadlift sticking point commonly occurs during the knee passing phase of the lift, with the bar in line with the inferior portion of the patella. To increase momentum for a given barbell weight, velocity must increase. Optimizing resultant forces through the sticking point phase will also help to increase the likelihood of a successful lift. Therefore, velocity must be maintained leading into this phase. While movements focusing purely on maximum velocity are commonly incorporated in powerlifting training, an area that lacks research is choosing optimal warm-up protocols for maximum velocity and performance in the conventional deadlift. Static stretching has been considered part of general warm-up routines in competitive sports and physical activity for decades. This entails stretching a joint to the end range of motion and holding that position. Physiologically, this increases the compliance of musculotendinous units, a practice commonly thought to alleviate the chance of injury. As a warm-up protocol, static stretching actually has little scientific evidence to support increased injury avoidance. Furthermore, this warm-up technique has been deemed an inhibitor on maximum strength and power in a multitude of studies. An investigation by Wilson, Murphy and Pryor, shown on the screen, established a distinct association between stiffer musculotendinous units and improved force production capacities of a muscle. For improved force production, a goal of stiffer musculotendinous units should be considered for deadlift warm-ups. In addition, support is building towards a concept called post-activation potential, which is shown to maximize acute power development in a study by Lorenz published in 2011. This study involved a strength exercise routine as a warm-up. These post-activation potential exercises dynamically progress into movement patterns similar to the desired performance action. A more recent investigation by Budafin and colleagues again confirms increases in performance through this warm-up method. However, these studies focus solely on weighted squat jump power. Therefore, a gap exists in the literature for how this preparatory protocol, especially when compared to traditional static stretching movements, affects performance in the conventional deadlift. This study aimed to investigate the effects of both muscle activation and static stretching warm-ups on vertical linear barbell velocity in the concentric phase of the conventional deadlift. From the evidence already mentioned, it is suggested that a muscle activation warm-up will result in an increased linear velocity. Therefore, we hypothesize that muscle activation warm-ups will result in increased linear bar velocity in the concentric phase of the conventional deadlift compared to a static stretching warm-up. A call for volunteers was put out to students from the Griffith University Biomechanics 1 course. Anyone without experience in the conventional deadlift was immediately excluded. Subjects were then asked to complete a physical activity readiness questionnaire, or PARQ, for health and safety reasons. If a student answered yes to any of the form questions, they were also excluded. The final group of volunteers was made up of males with a mean age of 20.33 years. For extra safety measures, an initial session was performed to confirm all participants' familiarity with the entire trial, and to allow for complete recovery, testing commenced 2 weeks after this session. Testing for both conditions was originally intended to be taken at Performance Training Centre Gold Coast, but due to unforeseen circumstances, Only the first muscle activation trial was tested there, and the static stretching condition had to be tested at University Fitness Health Centre at Griffith University, Gold Coast. Steps were taken to ensure that the conditions were kept the same between the different trials. This included using the same barbell, lifting off a similar surface material and raising the plates to the exact height as the original trial. Both sessions were performed in a fed and hydrated state, and all lifts were performed in accordance with International Powerlifting Federation rules. To collect data, a Sony Image camcorder was employed with a standard tripod. The camcorder was set to an identical setting across all trials, including 1/750th shutter speed, along with optical zoom and sports mode enabled. Camera angle was level with the ground and positioned in a sagittal plane to view each participant at mid-height level. Indoor venues enable easy, consistent control of environmental factors. These include background and lighting. Care was also taken to avoid parallax or perspective errors. The approximate field of view was duplicated across trials at around 2 metres. Strapping tape was placed at the end of the barbell column with a black circular marking, 1 centimetre in diameter, centred for video tracking. This marker, along with a calibration scale placed in frame, was integrated into Silicon Coach software for later analysis. At the beginning of each session, participants warmed up with a 5-minute jog, followed by a 3-minute recovery time. Then they commenced their specific warm-up routines. The static stretching and muscle activation routines were performed as outlined in the tables on the screen. These warm-ups were designed to either activate or stretch dominant muscles used in the concentric phase of the conventional deadlift. After the specific warm-up, participants took a 3-minute rest, then began deadlifting with triples at 40 kilos, 60 kilos, then doubles with 70 kilos, and finally performing 5 recorded trials each with singles at 80 kilos. The recorded data was analysed using Silicon Coach via the Griffith University Gold Coast campus computers. Each video was entered onto the software, then cut so the videos only included the necessary film. Once it was cut accordingly, the footage needed to be scaled to size with reference to the 1 metre calibration scale that was present in the frame while shooting. This was done with the Silicon Coach scaling function. After this, markers were used to pinpoint the moment before the bar left the ground and the exact instant the lifter was the most locked out, in accordance with the International Powerlifting Federation rules. This can be seen on screen. The vertical component of the linear bar velocity was then calculated. After this, the data was collected from the software. The data collected was entered into a Microsoft Excel spreadsheet as seen on screen, where the vertical linear velocity was calculated as change in distance over change in time. From here, the average velocity results from each subject were also calculated, therefore removing the need to use a Butterworth filter. After this, percentage difference was calculated for each trial within subjects. The data was statistically analysed using a paired t-test with a p-value of 0.05 to determine if there was any significant difference between the sampled data. Finally, variations in performance were compared across both trials through graphical representation. As you can see in graphs 1 and 2, all 3 subjects moved with faster linear bar velocities under a muscle activation warm-up than they did using a static stretching warm-up. Static stretching trials saw decreases in performance across all participants when compared with muscle activation trials. These drops can be seen in Table 3 as 12, 20 and 30% declines respectively. A t-test figure of 0.026 confirms the significance of the contrasting data. This study hypothesized that muscle activation warm-ups would result in higher deadlift velocities than static stretching warm-ups. The prediction was supported by the results, in particular Subject 3. It could be speculated that even though static stretching warm-ups increase the compliance of muscular tenderness units, that they are not the best for force production. The fact that these differences were so evident in our results reflects what was brought to light in Lawrence's research, that distinct improvements occur following a muscle activation warm-up. Furthermore, the findings are also in line with the concept of decreased force production with static stretching warm-ups, as discussed previously. The findings of this study support the hypothesis, however, several limitations arose that should be acknowledged. Although environmental conditions were controlled as tightly as possible, the unforeseen circumstance of having a venue change mid-study posed some issues. In the context of sports psychology, a new environment may have a boosted or hindered arousal levels prior to performance. Furthermore, the two lifting environments differed slightly in camera positioning, floor space, floor surface, and background movement or noise. Another hindrance was the assumption that 1 full week was substantial recovery time. Other issues include the small sample size of only 3 participants and lack of control variable to indicate whether the difference in trials was influenced mostly by a positive effect of muscle activation on velocity or a negative effect of static stretching on the velocity. Finally, only one method of data recording was utilised, and videography is an indirect system subject to parallax, perspective, human and equipment errors. Methodology aside, possibly the largest limiting factor to the real-world relevance of this investigation was the selection of participants. 3 young adult males conformed to a very select proportion of the population and failed to target the people that could benefit the most from this research: powerlifting athletes. Future studies could combat these flaws in the following ways. Firstly, by ensuring that the same venue is used throughout the experiment, and also by enabling for more recovery time between trials. As well as this, a larger study group and employing direct measurement systems like an accelerometer would provide more accurate data. Lastly, by testing other demographic groups such as powerlifters, relevance to real-world application will be increased. In conclusion, the resultant outcomes are as follows. A review of current literature on static stretching and post-activation warm-ups showed a gap in literature for powerlifting-specific movements. This study looked at the different warm-up protocols and how they affect the conventional deadlift linear barbell velocity, and showed benefits in the performance following post-activation potential warm-ups over static stretching with unanimous results. The results of the data are consistent with past research and suggest a crossover effect for conventional deadlift applications. In future research, flaws will need to be addressed to confirm this study's reliability, and in future, more investigation should be extended to competitive powerlifting settings.